we are going to begin our discussion of induced currents with something that's kind of in between historical and just our conceptual framework. So the book introduces this as Faraday's discovery. So he does an experiment and then interprets it. Now we're going to start with these observations, but then there's a few more experiments we'll talk about to really understand the phenomena we're looking at. The basic construct of the experiment is that there's an iron ring, and on one side of the iron ring there's a bunch of loops of wire that go around it, connects to a battery and a switch. On the other side of the iron ring there's a current meter, which then makes a complete circuit with a bunch of loops and comes back. So notice that on this side with the current meter there is no battery, right? And there's no electrical connection between what's on the right and what's on the left. So what Faraday noticed was that when you close the switch, you get a current. Now notice, and there's a few things that's really important here, that this is momentary. So I describe this as switch is closing. Don't think the switch is closed, so we get a momentary current. It's in the moment where the switch is first closing, that is when you get this momentary current. So this is very, very short in time. Then, as the switch stays closed, we have no current. So note that in this mode, we do have a current flowing on the left because we have a battery and a complete connection. But on the right, I equals 0. Now this is actually what you would expect, right? So this, I want to focus on this briefly. That there is no electrical connection between the circuit on the left and the circuit on the right. So in general, you wouldn't expect there to be any current flowing in a circuit where there's no battery. So this picture should make complete sense to you. No current is induced because there's no battery here. Why would there be a current? So it's really this first picture that's surprising, and then the last picture when we first open the switch, we again have an induced current, but notice that here it was to the left and here it was to the right. So you're getting an opposite direction. So you're getting, again, a momentary current. So this middle picture should make sense. They're electrically separate circuits, so if you don't have a battery in a circuit, why would a current flow? But the first and the third situation are the interesting ones. We see that when the circuit on the left is changing, something to a different circuit happens. So that's what we're going to try to understand. We're going to look at a few other experiments first so that we can make sure that our interpretation here is as general as possible. So the first experiment that we're going to talk about after those is actually really the same experiment but done in a slightly different geometry. So note again that we have a battery which gives us a delta V, but here we have no battery, right? So there are two different circuits here, but they both have a coil and the coils are aligned. So again, in the moment where you're opening or closing the switch, you get a momentary current here. Opening it makes the current go one way, closing it makes the current go the other. So this is equivalent to the first situation that I presented, Faraday's discovery. But here we're not using that iron coil, we're just putting these two circuits next to each other. So this is really identical to the previous situations, but the geometry might make a little more sense to you. So that's all that is. So now let's look at some different situations. Here we again saw that somehow the circuit on the left and the circuit on the right were interacting. We see that there are coils. These coils should make you think about solenoids, and solenoids should make you think about magnetic fields. So maybe this phenomena has to do with magnetism. So let's think about trying this just with magnets. So we can take a magnet, a normal permanent bar magnet, we can push or pull it into the coil. And again, we see that we get an induced current. Notice here again that it needs to be actively happening, right? There needs to be a push or a pull. If it's just sitting there, nothing happens. Again here, there's no battery. So where is the current, right? Remember that this is your current meter. Where is the current coming from if there's no battery. Somehow it has to do with magnetic fields, and again, you must be actively moving this magnet for this to work. If you just put the magnet in the coil, nothing happens. Okay, so it definitely seems to do with magnetic fields. We don't have to use a second circuit, we can use a magnet, and it has to be moving. Well, what if instead we used a fixed magnetic field, right? So this is a big horseshoe magnet, a big bar magnet, and we're actually going to be pushing or pulling the coil now in or out of that magnetic field. So you can think about there being a magnetic field. Remember that it comes from south and, it comes from north, goes to south, right? So it looks something like that. Notice that this wouldn't be exactly a uniform field. And so as we pull or push the coil in or out, we again get a current. And again, keep in mind that we must be actively moving it. We're only getting a momentary current. So if we just let our coil sit there, nothing happens. So one thing that I want to note is that experiment 2 and experiment 3 are very closely related. In one case, we're moving the magnet, and in one case, we're moving the coil. Now, depending on how you think about this, you might go, well, of course that's equivalent. It shouldn't matter if I move the magnet or if I move the coil. They're moving with respect to one another. And that's good reasoning. That's excellent physics reasoning. However, we're actually going to be discussing it slightly separately, at least initially. So one thing to be careful about is that in this chapter, we're going to talk about a few scenarios and phenomena as if they are different. And in the end, we'll say, oh yes, and they are in fact all the same thing. So notice that there is a very close relationship between all three of these experiments and all of the phenomena we're going to be talking about. So what is the conclusion? If a magnetic field passing through a coil changes, or is in the process of changing, you get a current induced in that coil. And again, it's momentary in that as soon as your magnetic field is constant, that current goes away. So that is our conclusion. Again, you might feel comfortable drawing that conclusion simply from Faraday's experiment, or you might need those three follow-up versions. We can do this with one coil creating the magnetic field and another one detecting it basically and having this induced current, or you can use permanent magnets. The rest of this chapter is going to be understanding this phenomena in detail.